Today's motivation behind this webinar is to understand like what goes on in the industry, how in current market, like despite COVID-19, why control systems are really in demand, what practices do industry really follow. And this is through this presentation, I'll try to cover how we implement control systems into actual vehicle systems, for example, suspension, engines, or anything. And today's agenda mainly will be discussing the background, like what is a control system, what technologies are basically in demand right now, what is the future market, even if there is some effect of COVID-19, how autonomous systems are under research and being developed by various giants in the industry. What are the job prospects for people who are working in this industry or want to start within vehicle control systems? Then some of the example and a case study regarding how we can create a control system using the practices which are generally followed in the industry. The first question is, when I heard about control system, was what is a control system, like what it is actually. So if I tell about control system in a general way or in a simple manner, it is a mechanism basically that we employ to get this output which we want from the system. So for example, if I tell you, if you have a box, or right now you are using your mouse or TV screen or your laptop screen. So suppose you want to move the laptop for some displacement and you are not sure how much force should I put to move that laptop for at particular angle. Now control system can actually help you basically using a logical algorithm which you create or derive, and using that algorithm you can actually make your laptop move to that particular angle, but just by putting that input, like you want 20-degree angle or 10-degree angle of your screen. And control systems in general, they are of two types. First is open loop control system and second is closed loop control system. So what I mean by open loop control system and closed loop control system is, an open loop control system, it doesn't have any kind of feedback. So you just start the machine and it will keep going on. It doesn't know like, has it reached the desired output or not. For example, consider again your laptop screen. You want to move the screen at 20-degree angle, you'll put the input, but the system won't know, is it 20-degree? Did it reach there? It doesn't know. But in closed loop system, it will actually take that output angle and it will again send it back to the system, telling it that the screen is not at 20-degree and it's at 15-degree. So that is a very simple description or a difference between open loop and closed loop system. There's a lot of low level details involved in it, but right now we'll get back into details. But right now it's a general difference. Like if there is a feedback, it's in closed loop. If there is no feedback, then it's an open loop system. And some of the examples which are widely used in automotive industry as well as other industries are proportional, integral, and derivative controller, which is our PIDs. Then we have state space controller, model based controllers, which can use any algorithm depending on your model, and then machine learning based controllers, which can be classified, regression based, or even decision tree models are involved. So if you at present, if you are not aware of these terms like PIDs, state space, don't worry. It's just a way of designing a controller using the system model or without a system model. It's just the control system jargons right now if you are not aware of it. So moving on to the next slide, which is why do we actually need control systems? Even if you are aware of control systems, why do we need it in vehicle? Like I'm fine driving my vehicle by myself, I'm fine with how it is performing right now, then why do we need it? So basically there are government legislations and even industries, they are striving, because of the competition in the market, they are striving to give the best performance, best comfort, and most amazing experience to the people who are driving their vehicle. And in terms of providing that kind of satisfaction or the facility to to its customer, companies are working on automatic controls in terms of fuel efficiency, in terms of safety, for example, automatic deployment of your airbags, which is very complicated when you try to do it without based on just a normal algorithm. But if you are aware of your system, how it is acting, that under what situation, how is it acting in different situations, then you can actually get the best output of your system. And that is where your control helps your vehicle. In terms of emission, for example, the government has declared in Euro 6 norms and 7 norm that there should be almost 0% of nitrous oxide. So how can you actually attain that using the catalytic converter you have? How can you control the amount of combustion taking place? Those kind of things. And then there is one important race which almost all the companies involved in autonomous vehicles are running for, and that is the level of autonomy, which is defined by SAE as the way how you are controlling your vehicle or the way how it is able to control itself, basically the self-driving vehicle. So there are 6 stages of a self-driving vehicle. The first one, which is the level 0, it's a normal vehicle which have been in the market since like 70s or 80s, which is like it involves only like anti-lock braking system or your cruise control. And then you have the first level vehicle where only one particular dynamics of the vehicle is controlled. It can be in the lateral direction, which is in your y direction, or it can be your longitudinal direction control, which is in your x direction. What I mean by lateral or longitudinal control is, if I take an example, you have automatic cruise control. Automatic cruise control is basically you try to maintain the distance between you and your the other vehicle which is in front of you, and it actually maintains the speed with respect to the vehicle, so you do not get close to the vehicle when you are driving. And that is like you are maintaining the dynamics of your vehicle in the x direction, so it is considered as longitudinal vehicle control. And one of the example where one of the car which has longitudinal control is, we can say, the vehicles which are already in the market. For example, Honda has it, then even Maruti, Tata, they have it. And then the third stage or the second level of autonomy is where there are both the controls. So your vehicle can be controlled longitudinally as well as laterally. And one of the example is your Tesla autopilot. Then the third level or the fourth stage of autonomy is when you are, it's not just the longitudinal or lateral control, but you can actually allow your car to drive itself. And though you have to monitor it continuously, but your car can handle it itself if it wants to drive on the road, or if it wants to tackle the disturbance coming on the road, avoiding any kind of object or a passenger. But it's quite a risky stage, so most of the company, what they're trying to do is they're trying to achieve the fifth stage or the fourth level of autonomy, where the human doesn't need to monitor the car continuously. It can do some other activity, reading a newspaper or working on its own, working by side, but the vehicle will keep running, will keep driving itself. And then the stage or the final stage of autonomy, where you don't even need a steering vehicle or pedals, the vehicle will drive itself. We are actually there, but most of the companies, they are scared to deploy this level right now in the market. Most of the companies except Tesla, because Elon Musk is futuristic and courageous as well. So other companies like Volkswagen, BMW, they want to skip from the fourth level to fifth level, which is the high automation stage, because it's very convenient. Either the machine will be responsible for the complete driving, and human can actually do something which they want. So yeah, like, though we are on the fourth level of autonomy, we are planning to achieve fifth level of autonomy by the year 2025, and most of the vehicles, they have already started testing and track level testing, basically, just to verify like how safe it is right now. And going to the next slide, I would like to show some of the examples, the level of controls we have achieved. And one of them is Volvo's truck example, which is quite famous. You might have seen it. So I'll tell you what's going on. Just enjoy the video for this 1 minute right now. So what you see here, it's the steering control, just how skillful both are, the stuntman and the, okay. So as you have seen in the video, the guy was splitting between two trucks which are highly stable while reversing. Now, let me tell you, reversing a truck is a very complicated phenomena. It comes to controlling its dynamic behavior. It's very complicated. Like, there have been research for quite a long time. It's been like, still we are trying to improve it. And through this video, we were just showing one of the most amazing feat we have achieved recently. Like, this video is from 2017, I assume, and we have achieved this feat, and Volvo is trying to show like how smooth its reverse stability control is while reversing the truck uh, through its lateral control. And like there was, it's just amazing. So this is what you can achieve using the controls which we are going to study, or which we are going to see how it works in the industry today. And then there's another video which I'll leave for you to find on YouTube, because it's a self-drifting car designed by BMW and its students. So what is the current market basically going on right now? There has been COVID market crisis, autonomous system, the companies involving with autonomous system, they are trying to figure out like how can we recover from this market, the existing change in the demand. But let me tell you, so the research and development is in autonomous system, it's very demanding, like it's still at rise. Companies, they are still involved in it. A lot of companies, they want to deploy their autonomous vehicles or new technologies involved in the autonomous systems onto the road in the coming years. And why? Because I'll talk about European infrastructure first, which is like more than 40% right now compared in Europe. Like more, the main reason is the European infrastructure, the European roads, and even the people, they are quite open to adapt to autonomous systems. Consider Norway, consider Sweden, consider Netherlands, Germany. They prefer autonomous cars compared to the manual cars. And which is against the American culture as well, because Americans, they are more like petrol head people. They don't they don't like petrol, they don't like electric cars, they don't like autonomous cars to drive. They feel like the authority should be with them. But Europeans, they are quite open to this thing, which is like the biggest market we have right now. And the development in that is expected to boost. Even though there is COVID-19, it is expected to boost from $16 billion, which is right now in which was right in 2019, $37.22 billion by 2023. Just because the technology is developing, there are various companies involved in developing the sensors, the processing powers for autonomous systems, and everything is taking place in a very fast-paced manner, that soon we are actually going to see that COVID is not actually having the effect on the development of autonomous systems. And when the market is still there, when the companies are still investing in autonomous system development, then you have a lot of prospects as well. And that is the same thing with control systems, because the market is still active and there people are still looking forward to driving autonomous cars, especially in Europe, in Asian regions. In India, the infrastructure is a problem, but people still, they are enthusiastic for this kind of cars, and a lot of companies, they are involved in it. What kind of jobs you can have with, if you know control practices, if you know how to design a control system. So there are different designation, but the core function is that you are going to design controls, whether it's through testing, whether it's through improving the performance of your system, or meeting the legislation required to pass your vehicle into the market using functional safety. So now we'll come to the main, the theme of our webinar, which is control system design. We'll try to get into details, and this is the depiction or a small schematic or a simple schematic of how a closed loop system looks like. And basically, just to tell you, this is a controller. It can be any kind of control action which we want to deploy. And by plant model, I mean your system. It can be your brake disc, it can be your suspension, it can be your entire vehicle. It depends what you are considering as your plant model, what dynamics of your vehicle you want to control. Is it the speed of your vehicle? Is it the fuel? Is it the consumption of your fuel? Anything which you want to control, you try to model it. So that is considered as our plant. And this is our feedback sensor. It is basically the feedback coming from our plant or the system which we are trying to control. And it can be any sensor. It can be your hallmark sensor, it can be your torque sensor. Whatever system you are using, according to that, you will have a sensor to send the signal to your controller that there is some kind of difference between your actual output and the outputs which you are giving in reference. I hope my audio is there. You compare it with the input reference which you give, and then this little part here, it's error which is taken as input to your controller, and then the controller manipulates the input which is to be sent to the plant model to get the desired output. Without pictures, uh, it's a simple schematic to explain. Then what parameters or what performance parameters do we consider when we try to design a controller? That is the most important question. If you are designing a controller if you are designing a controller in the company for a system, this is the first question you have to tackle. while presenting your plan, that how you what you basically are trying to solve, what is the actual performance problem that you are trying to solve, whether you want to increase the system response, whether you want to actuate that system automatically. So those kind of things you have to present in terms of these parameters. And these are the six main parameters, I would say, the most important parameters for a controller, and I'll go through them. So the first parameter which we consider while designing a controller is the steady state error. Now what does that mean? So steady state error basically is, if you see this blue line, it is our output which we have received after deploying the controller, and the black line, it is our desired output which we want. So suppose our desired output we want 1, but the final output was 0.8, then our steady state error was 0.2. So the difference between the output we want and the difference between the output we have. So that is steady state error. After that, if we see this thing, the delay time, it is how late your system is actually responding. Now there are several definitions for this, but the most widely accepted definition is that the time taken by a system to reach the 50% of its output, the 50% of the final output, that time is considered as delay time. Now delay time is mainly because of the system's own dynamics. It can be its inertia, it can be the initial state it tries to cover up. So delay time can vary, and most of the control designers, they try to reduce the delay time so that the system is sensitive and it can respond as fast as we want. Then the rise time is basically the 90% of the final value. When we reach the 90% of the final value, we consider that as the rise time. Accordingly, the peak time, when you have the maximum output at some particular time, that is considered as peak time. And the difference between the percentage difference between that value and your desired value is considered as overshoot. And then this settling time, which is one of the most important factor, I would say, especially when I have been designing it. Most of the time you want your system to get stable and reach that value within some desired time. So this settling time is the time taken by your system to reach the bandwidth or the threshold of your final value. It can be zero point 0.5, or it can be 3% to 5% of your final value where you reach, and that is considered as settling time. So you can see like there are oscillations, but it's settling at somewhere here. So around 6 seconds is the settling time. And after considering the performance parameters, what we try to do, we can deploy a controller. And one example is the PID controller, which I said in the beginning of this webinar. So what is a PID controller? It has three terms. It is a proportional term, there is an integral term, and there is a derivative term. Now, if you are not familiar with PID control, then I would like to discuss briefly about it. So proportional term, it's like a constant which multiplies with your error, and then it amplifies the signal basically. So suppose you are getting this green response, or suppose you are getting this dotted response, which is without your control. So what will your proportional will do? It will calculate the error, send it to your controller, and then again multiply or penalize it, which is like telling your system that there should be more input to get the response which we want with respect to our requirement. Thus proportional control will act, and you will have the response which is in red. Now what you can see is the proportional controller, it takes quite a time to respond, and second, it has oscillations in it. So what we try to do, we go for, and then the most important thing, there is a steady state error. So what we try to do, we try to add another term which is integral term, and then we have the green response which still has some oscillation, but finally are able to minimize the steady state error. It's almost zero, almost. If we zoom out, then there will be some error, but it's almost zero. And if the effect or the impact of integral term is the overshoot will increase, but the steady state error, it drives it to zero, basically integrating your error to reach the 0 point or to minimize the steady state error. Then if we want to reduce the overshoot as well, then we go for we add the derivative term as well, which actually reduces your overshoot and makes it stable or settles the response faster. And you can see it is having the most optimum response compared to without controller or with a PID controller. The PID controller is having the most optimum response. So without going into the mathematics, this is how the PID controller actually works, having different terms creating different effects on your system response. And once you know, so there are several controls, but once you know that what controller can have what effect, you can actually decide a control strategy. And talking about PID controller, it's mainly used to improve the system response, like fastening it or slowing it down as per your requirement. And today's case study, we'll try to design the same PID control for a semi-active suspension. Now, suspension, we all know, if we are familiar with automotive, that there are three types of suspension, and it's active, semi-active, and passive. So passive is your most conventional suspension system, where you have just your normal damper and spring mechanism to absorb the vibrations coming from the road, but it does not create any additional change in your chassis to absorb the vibration. It's just mainly from the road. But when it comes to a semi-active suspension, it has an additional actuator which varies the force to absorb the vibration coming from the road or the disturbance when your vehicle or the wheel is going across that vibration, across that disturbance. And then your active suspension, which actually displaces your system or your chassis to absorb the vibrations. So it was some small history or some brief history about semi-active suspension. It was developed by Delphi Technologies, and the main reason was that though passenger are more inclined to having better comfort, handling is an important part when you drive a car. So semi-active suspension was designed or developed to focus on getting comfort, but still maintain the handling part. And you can find it from in a motorbike as well as in cars. And what so we already know the system which we are trying to control. Then the next step will be to analyze the requirement. What do we want, and then accordingly how should we proceed? So basically, when we do a project in control systems, the most widely accepted development life cycle is a V model, which is because the way it looks, it's in a V shape, and you start from requirement, creating the requirement or defining the requirement as per the specification you have from your client or your in your project, and you gradually move to modeling, simulation, implementing the control, then different type of simulations, and finally doing the testing on the actual system. Now, why we are using V model in today's webinar? Because it is widely accepted in industry as well. Like, so the companies I have known in my college, in even during work, they widely they most of the time they ask if what kind of model do I use to implement my controller, and it's most of the time it's the V model. So today also we are using the V model to deploy controller into our semi-active suspension system. Now we'll start with requirement. What requirement do we want for our semi-active suspension? Now we will start with a very simple requirement. We won't focus on a lot of performance parameters. That's true. Vibration is the most important parameter. If you want to control the vibration, then only the passenger will feel comfortable. But we are also focusing on the handling part today. So yeah, we can focus on vibration if our focus is on comfort. But for handling, we'll try to also focus on the displacement between the sprung and the unsprung mass, which is your suspension travel. And accordingly we'll move forward. So if I take this system, which is our semi-active suspension system, and if I try to create a free body diagram, this is how it will look. If I take only a quarter car model, like if you're not aware of the term quarter car model, it is 1/4 of your entire vehicle, just the wheel part, and it's a part above the suspension basically. So it's the 1/4 part of your vehicle, and if you draw free body diagram of that, this is how it looks. And what does this terms mean? So basically, this is our road, and as soon as our vehicle it travels over this road input, there will be some excitation. So this is the displacement caused by the road, which is our ZR. And then when your unsprung mass is displaced upward because of the excitation, it's the unsprung displacement, and then accordingly sprung displacement. And then K is for your spring stiffness, C is for your damping stiffness or damping coefficient, and then FD is your force by your variable damper or the force actuator. And we have considered a very simple model. Basically, we are not considering the friction, we are not considering the damping in your tire, because when we start modeling using the for a controller in a software, we usually consider a very simple model, which can represent our the system dynamics, but which can also help us to start or to go with the initial development of the model. Now, why? Because you can keep tuning your model, but you will have some, as per your requirement, you will have the model, and you can keep tuning it the more you have a requirement from the same model. So for example, right now our focus is just on the displacement between the suspension and the between the sprung and the unsprung mass. So we don't need the friction right now, we can ignore that. We can ignore the damping coefficient from the tire, and accordingly we have modeled this thing. So the equation of motion, it will look something like this. And how we derive it, it's just the Newton's law of motion. So in sprung mass, you can see there is the weight of your sprung mass, which is loaded because of the gravity, because of its own weight. Then you have the spring stiffness, but then the displacement is from your sprung and the unsprung mass. So accordingly you will create the equation. So you start with the force you have, and then the damping stiffness between the sprung and the unsprung mass, and the spring stiffness between the sprung and the unsprung mass, and the load, the effect of its own load. So accordingly you create these equations. Two equations we have, which also signifies that it has 2 degree of freedom. It can move, our sprung mass as well as unsprung mass. They are the like, it has 2 degree of freedom. Then moving to the modeling part, this is how our model will look like, but let's do it in Simulink.